Everybody. I'm going to take my mask off just so you guys can hear me, but I promise I will stay 6 feet away from you. I promise. Yeah, it may. So welcome all. Welcome to the first
Super Stellar Friday.
Okay. But yeah, thanks for coming. I'm Mark Ryan, and I'm going to speak a little bit tonight about mass extinction, what it is, when they happened, who didn't make it. A little bit about myself. I am actually a full-time professor down in Massachusetts at Northern Essex Community College. I was a teacher occasionally up here at NHTI, and also a permanent educator here at UCAM. I describe myself as a science nerd, and I'm totally comfortable with that. I've always loved all things science ever since I was like, yay tall probably. And I think I'm just one of those people that's been very lucky to be able to do everything in the sciences ever since I was. So the question that I get from a lot of people is, why is it that I'm so interested in mass extinction? So when I really think about it, I can kind of go back to this particular image. This is an image from a book I remember reading as a kid, which happens to be this book right here. It's called Dinosaurs, the Golden Exploring Earth book. There we go. And within the pages of this book is this particular drawing. And the page itself talks a little bit about why did the dinosaurs go extinct? Now, the thing about that is that this book is from 1973. So it's a ways back. And this is before we came up with the idea that the Earth had been struck by an asteroid, which ultimately led to the demise of the dinosaurs. So the book just talks a little bit about gamma rays, wiping everything out, or being able to eat dinosaurs, whatever the case is. We simply didn't know. And I think that just always fascinated me. And so I kind of always pursued this subject. So, all right, so let me start. The first thing that we really need to make sure we're all on the same page for is understanding what exactly is it we mean by a mass extinction. Okay, so when we talk about a mass extinction, there are 3 criteria that we look for. Okay, for something to be classified as a mass extinction, first off, it has to be global. Okay, it cannot be a regional event or localized event. It has to affect everybody across the planet. Okay, so that's number 1. Number 2, a mass extinction occurs in a short period of time. Now, when I say a short period of time, a lot of people are probably thinking, okay, well, we're talking hours, weeks, months, maybe years. No, we're talking tens of thousands, hundreds of thousands, probably the millions of years. So how can I call that a short time frame? Okay. Well, what we're doing is we are comparing this to the age of the Earth itself. So the Earth itself dates back about 4.6 billion years. So we're talking about 1 million years at 4.6 billion years. That's a pretty short time. Okay, so that's what we go with based on time frames. Lastly, mass extinction will affect upper level taxa. So you may remember from your high school biology or college biology or biology class you may have taken, the Linnean system of classification. Kingdom, order, family, genus, species, right? When we're talking about mass extinction, we're not talking about species going extinct or even gender going extinct because that's too low on the system. We are talking about families going extinct, orders going extinct, and in some cases even classes of organisms going extinct. Okay, so it has to be higher up in the living system, not for the body. So as long as we hit all 3 of these criteria, we can think of an event as being a mass extinction. Now, why do organisms go extinct? Good question. More often than not, when something is going to go extinct, it's because of some kind of stress in the environment. Okay, so when the population is stressed, or a species, or whatever the case is stressed, they have 3 options. Okay, number 1, they can adapt. Number 2, they can move to a less competitive environment. Or number 3, they go extinct. Now, we do want to keep in mind that this is not something that happens like that. Okay, this is going to happen over the course of generations. Because adaptation doesn't happen right away. Right? Moving to a less competitive environment doesn't happen right away. Okay, so it is going to happen over a period of time, but those are basically the options. I'll take questions at the end. So this right here is an example of something we call a sea lily, which is a form of a cryoid. It's an old organism, and they still exist today. When you look at this image here, you can look in the background, see that it's very dark. And that is because this type of critter today lives very deep in the ocean. And it lives deep in the ocean because it's less competitive, fewer predators, it's not as hard to acquire food and whatnot. But back in 200 million years ago, these things dominated the ocean. We have massive fields, if you will, in the bottom of the ocean, fields of these things. So they used to be really, really dominant, but they've been pushed back to a less competitive environment. Now, what causes a mass extinction? Okay. A lot of things can happen that can ultimately cause extinction to occur. And more often than not, it's going to be multiple events, not just be one single solitary thing. The things that may occur that can cause mass extinction, global climate change. Okay. The one thing that we find about the Earth's atmosphere is that through time, it is constantly changing in regards to the levels of carbon dioxide as opposed to oxygen. Two of them are actually inversely related. CO2 goes up, O2 goes down, CO2 goes down, O2 goes up. Okay. So when this happens, this causes global warming or global cooling. Okay. So when that happens, this can stress organisms and can ultimately possibly result in extinction. Changes in ocean currents. Okay. One of the beautiful things about living here in New Hampshire, aside from the people, of course, is that we have a very temperate climate. Okay, it is very nice, fairly warm in the summer, but not too warm. It's to be delightful sometimes. Winters are cool, but not too cold. The reason for that is because we have that nice current right off of our east coast called the Gulf Stream. The Gulf Stream originates along the equator, works its way northward, and takes all that warmth and brings it right along with it and gradually releases it, helping to regulate our climate. Now, you think about somewhere like the Dakotas. Okay, you go to North and South Dakota in the wintertime, it is freaking cold. Okay, you go to the Dakotas in the summertime, it's freaking hot. Okay, and the reason for that is because those are on the inside of the continent. There's no ocean current to help to regulate that climate. And as a result, it's not as comfortable as here in New England. Okay. Sea level change. This is something that's been going on since day one. Ocean water warms and cools, expanding and contracting. We see increases and decreases in the rates of plate production. So what this does is it causes sea level to rise and to fall. When sea level rises, areas that were once in the what we'll call photic zone, exposed to sunlight, something that's going to get dark. They can't photosynthesize. Okay, or sea level drops and exposes vast sections of continental shelf to the air. And if you're an organism that likes water, that's a problem. Okay, so you're probably going to go extinct. Increased volcanic activity. Okay, when we talk about increased volcanic activity, we're not talking about something like Mount St. Helens or Mount Pinatubo or Mount Etna, just a single solitary event. What we're thinking about are what are called large igneous provinces. And these are areas where you see massive extrusions of lava, and we're talking tens, hundreds, thousands of cubic kilometers of lava being extruded onto the surface of the earth in a relatively short period of time. Now, when this happens, you also release a lot of CO2. And so what happens then is you start getting global warming, which ultimately lastly, extraterrestrial causes. All right, these are the fun ones. These are, oh my God, that's so cool. You know, the Earth gets struck by an asteroid. Isn't that fun? Yeah, okay. Well, we do know that the Earth, of course, is struck by asteroids and comets. You can look around the Earth, you can see craters, you can see evidence of this. and they can potentially lead to extinction events. There are some proposed that something like a supernova explosion is close enough to the Earth, within like 500 light years. I know, close. Could potentially bathe the Earth in gamma radiation and potentially lead to extinction events. Kind of hard to find on the fossil record, but you never know, it's a possibility. So certainly extraterrestrial causes can lead to extinction. All right, so when we talk about mass extinctions, we talk about what are called the Big Five. All right, the Big Five mass extinctions that all occurred within what's called the Dinosaurs eon. Now, the one thing we do in geology is we break the Earth's history down into discrete pieces of time. We have what are called eons, eras, periods, and epochs. Okay, eons encompass the greatest amount of time. They can encompass hundreds of millions, in some cases even billions of years. Okay, good size chunks. We then have eras, so we can break our eons into eras. Now, right now, we are in what is called the Phanerozoic eon. The Phanerozoic eon is broken into 3 eras. Did I mention there's going to be a quiz when I do? Okay. So the Phanerozoic eon is broken into 3 eras. We call the Paleozoic, the Mesozoic, and Cenozoic. Those simply mean ancient life, middle life, recent life. Okay. And then what we can do is we can break our eras down into periods. Periods typically encompass tens of millions of years, maybe down into just millions of years. Okay. And when we talk about our mass extinction, we talk about them relative to periods. We do have epochs at smaller subsets of time. And in this case here, this is what we're talking about hundreds of thousands, maybe the million. Okay. But the Big Five mass extinctions that have occurred within the Phanerozoic eon, so we're talking about the last 540 million years. Okay. So the 3 of them are what's called the Ordovician Silurian. We have what's called the Devonian, sometimes called the Frassian Flammarian, if you want to be technical. We have the Permian Triassic, Permo-Triassic. We have the Triassic Jurassic, and then you have the Cretaceous Tertiary. Okay. You might recognize some of the names. That's good. All right. So what we want to do is we want to look at each one of these extinctions individually. What did the Earth look like? Who was it impacted by the event itself? And then what was the cause? All good questions to consider. So let's start with the Ordovician Silurian. So this is about 445 million years ago. All right, so a little while ago. And what did the Earth look like at this time? Well, if you look at a map of the Earth at this time, this is what we would see. Okay. One thing that you notice is that all of the land, or the majority of it, is in the southern hemisphere. A little bit opposite of what we see today. Today we spend most of the land is in the northern hemisphere. So a little bit different at this time. The other thing that we see is that we have a lot of continental shelf off the edge of continents, which is good for marine life because that's where they like to live. One thing we do want to mention, I do want to mention here, is that there's virtually no life on the land yet. Life has not made that transition. There might be a couple of plants hanging out, but for the most part, the land totally barren. So any life that we're thinking about is going to be marine type life. Okay. All right. So that's what the Earth looked like. So who went extinct? Well, these are some of the names. You have this particular critter here, which is called a brachiopod. And it's specifically called an inarticulate brachiopod. Now, brachiopods are kind of cool. Okay, I mean, everything's cool. So the brachiopod consists of 2 shells, kind of like a bivalve. Okay, but what's different is it has this little structure on the backside called the pedicle. So what happens is the brachiopod sits on the floor of the ocean by the pedicle, and the 2 shells are up on top of this, opening and closing, sucking in water, sucking in nutrients, and then whatever else gets in the way. Okay, they're not huge, so they don't have suck up vertical. But again, these particular groups, the inarticulate brachiopods took a pretty heavy hit at the family level. So we see quite a bit of them, quite a few of them get knocked out. This is the trilobite. Trilobites dominated the ocean for a long time. These are a type of arthropod, so they're related to insects and crabs and lobsters. Those are the big things. Okay? Well, the brachiopods were really dominant, but they took a pretty heavy hit as well during this particular extinction. Particularly the ones that are really strongly ornamented, all kinds of crazy structures and stuff like that. They really suffered through this extinction. We have what's called the horn coral, okay, which is what this is right here. This is a solitary coral. When we think about corals today, we think of things more like this, okay, what we call a scleractinian. And the coral makes up these massive colonies, okay? These were solitary. These were all by themselves, but they were all over the ocean. But these particular coral took a bit of a hit during this particular mass extinction. You guys want to see it? So pass it around.
Yeah.
I'm just making sure. I'm going to hold my breath. So that is what is called a horn coral. Okay, and again, they took a pretty massive hit during this extinction. And then lastly, we have these things that are called conodonts. Conodonts are really enigmatic because the only way we know they exist, or for at least until fairly recently, is through their teeth. Okay, now these are actually vertebrates. Okay, they have a backbone, just like us, but they're soft bottom. So the only things that get preserved are their teeth. And they're only about these big long. So the teeth are not very big. They're hard to find, but they took a hit as well. So what caused this extinction? Well, probably the biggest cause of the overall extinction event was because of glaciation. We had an ice age at this time. Okay? So we had continental glaciation, which would have resulted from global cooling. So CO2 levels down, oxygen levels were up. Okay, the planet cooled down, glaciers advanced. Okay, the major continent was on the South Pole, so that's where the big glacier would have been. And the other thing that would have happened here is that when the glacier grows, well, it's going to get the water from somewhere. So where's that water come from? The oceans, right? So when the glaciers advance, sea level drops. Sea level drops, and you got lots of continental shelf. Guess what? You got some extinction that's going to happen. Okay, so that's the most likely cause of this particular extinction. The next extinction is called the Devonian extinction. Okay, we're getting a little bit closer to our time here. We're now only 370 million years ago. So what did the world look like? The mass of the world, and this is what we see. Continents are starting to get closer together. What's eventually going to happen? Pangea, right? Eventually we're going to get Pangea. There's still a little ways in the future. But the continents are starting to come together. And so, yeah, we can start thinking about how that's going to happen. Okay. So this is what we're looking at here. Again, most of the land is still in the southern hemisphere. Okay. And as the continents are moving, what they're doing is they're altering ocean circulation patterns. And again, that moves to extinction. Okay. So we see that going on. Now, who did make it? Well, hey, look at that, trilobites again. They took a hit the first time, they took a hit again. Okay. So many families of trilobites were wiped out by this event. We also see that the coral, there are coral with some pretty heavy hits. So we have a couple of different kinds of corals that we look at. You have the first one that I had a friend like the horn coral, and then you have these kinds here. Okay, these are what are referred to as tabulate corals. This is a hexagonaria. Okay, and this is a fabocytes. And the one thing you'll notice about them when I hand them around is when you look at their cross sections, they're roughly six-sided. Okay, now, these dominated the reefs. And when the extinction hit, these are the kind of critters that were hit hard. Okay, pass around again. There you go. Last thing that we saw going extinct were the critters that we call the glass sponges. Now, glass sponges are made of glass. Okay. I don't know what you guys know about sponges, but sponges are living things. But some people know that, some people don't. Okay. But glass sponges, when you look at the name of a sponge, they actually have these little particles that are called spicules in their body. And they are colloidal. And the spicules that we find in the glass sponges are made of silica. Okay. So it gives these pigment critters a very delicate structure, which is why we call it glass corals or glass sponges. But anyway, so yes, those critters here also took a hit. Okay, so we see a little bit going on here. Now, all these are on the family level. Okay, so on the right criteria for mass extinction. What caused it? What caused it? Well, sea level change. That was a big one. Okay, they played again with the cooling events. So there was glaciation. So there was a reduction in sea level. That definitely led to some form of extinction. Now, there is evidence of a crater at this time frame. Okay, we have actually found a crater in Sweden that's about 55 kilometers in diameter. So there was an asteroid impact. So the question is, did that impact have anything to do with this extinction? We're not really totally sure. We're still kind of thinking about that. It's a fairly small crater, 65 kilometers long. That's nothing. But, you know, it may have had something to do with it, but no one's willing to put it on that quite yet. Okay, so we get to the third mass extinction. This is thought of as the granddaddy of all mass extinctions, because this one was massive. Okay? 250 million years ago, and when we look at how much of life went extinct, we find that 97% of all species went extinct. 97%. I used to teach large classes and I taught to change medicine. And I had classes of 100. I had everybody stand up. Not you guys mentioned this, not us. But I have all 100 students stand up. And then everyone sat down except for 3. Those are the 3 that made it. Okay. Pretty scary. Pretty scary. If there was ever a time when life wasn't going to make it, this was probably the one. Life's resilience. Life made it through. So by the time we get to this time frame, by the time we're at the Permo-Triassic, 255 million years ago, we have the full formation of Pangea. Okay, Pangea means all life, all time. It's a term that was coined by a gentleman by the name of Alfred Wegener. And Alfred Wegener came up with the hypothesis of continental drift, which is the precursor to plate tectonics. Okay, back in the early 1900s. So all land comes together. Very little ocean circulation. There are minimal ocean circulation. There are huge gyres out there. The ocean circulation is very, very simple. Okay. So because of this, and also the other thing we would see is a reduction in the amount of continental shelf because the continents have all come together, which again also leads to the potential for extinction. So who didn't make it? Hey, look, the trilobites again. Guess what? That was the final straw right there. They did not make it through after this. This was the end of the trilobites. The trilobites are a class of organisms. So when you're thinking about that taxonomic system, we're talking they're near the top. Okay, so that was pretty bad news. Again, some of our corals take a hit. Yes, the phagocytes rolling around there were more tabulate corals. The horn coral also went extinct as well. We call our those corals. This guy right here. It's called the Eurypterid, also known as a sea scorpion. Those things could be up to 7 feet long. Okay, they have large claws, mandibles. If there's anything that would scare you, that would probably do the trick. Definitely things out of nightmares. I have a small one here. Okay, a couple inches. They were this small too. It's okay. But yeah, the big ones, yeah, your best bet, run. Luckily, they were gone. Luckily, they are gone. They're all they went extinct after that PG boundary. On land, probably one of the most more well-known extinctions are what we call the pelvic sailbacks. Okay, like a dimetrodon. Just to be clear, not a dinosaur. Okay, can't say how often I see packages of kill these toy dinosaurs, and I see that in there. Oh my God, lose my mind. Not a dinosaur. But anyway, so we are looking at these organisms here. We are looking at classes of organisms. We're looking at families. We're looking at orders for the sponges, or the coral rather. So yeah, it was a pretty bad event there. But again, remember, 97%. I'm scared. So what caused it? So again, we have a full formation of Pangea, which again would have resulted in some form of climate change. More than likely, once all the continents were together, we would have massive deserts in the middle of the continent, you know, the size of the Sahara. And if you've been to a desert, you know that they're not super conducive to life. You know, things don't like deserts. That definitely would have led to some pretty serious extinction. Ocean circulation patterns changing. Again, climate isn't quite as pleasurable as it might have been beforehand. That's going to lead to an extinction. And then lastly, this is where we find one of our large igneous provinces, sort of a massive outpouring of lava. We have something that's referred to as the Siberian Traps. The Siberian Traps. So that's where the Siberian Traps were located at the time frame, and that dot is pretty representative of how big they were. Okay, so we're talking thousands of square kilometers. Okay, we're talking thousands of cubic kilometers of lava being ejected from the Earth. And then the resulting CO2, and as a result of that, simple climate change. So yeah, so this was not a fun time to be around if you're a living thing. All right, so we get to the next one, the fourth one, the Triassic Jurassic. Okay, at the end of the Triassic period, just of the Jurassic, about 210 million years ago. It's interesting because we're only looking at about 40 million years between this extinction and the previous one. Life recovered pretty fast, and suddenly it's hit again. Not fun. So the Earth still looks kind of weird, but it actually you can start to see some identifiable features. Okay, right here, right there. That is the beginning of the Atlantic Ocean. Okay, so Pangea was starting to show signs of splitting up. Okay, which is good. We like that. So Pangea starts to split, and we can see the edges of North America over here. You know, Africa, the North Coast is up around here. You know, Antarctica is down here. So it's starting to look a little familiar. I know. I'm probably pushing that one. So what makes sense? Always a big question. All right. So immunoids. These guys here. Immunoids are these absolutely fascinating critters that are related to octopus, squid, and nautiloids. Okay. They're very interesting, not just because I think they're interesting, but they're really interesting because they're composed of multiple chambers. Okay. They have all these chambers that make up the shell, and then they have a special tube that runs through called a siphon. And what they can do is they can easily adapt the pressure within the chambers themselves. So that allows them to move up and down through the water column. The other thing that they can do is they can jet around like an octopus or a squid. So you can jet around fast and you can move up and down the water column fast. These things were aggressive. These things would have been some pretty top-notch predators more than likely. This is a whale. This is a tiny one. There are some that have 5 or 6 foot diameter. Okay, so these things are definitely a lot bigger. I would have brought one of those, but it's really heavy. But 6 feet. It's taller. That's why it's so smooth. Just so you clear things like that. I didn't buy it like that. Yes, I love it. I didn't buy it like that. I know I did buy it like that. No. Okay. Anyway. We can also see these guys here. These are called dinosaurs. Dinosaurs were herbivores. They look pretty scary. But they're herbivores that are related to crocodiles. And they have spines, they have armor, and they're about that big as a person gets for some scale. Okay. So these guys, they went extinct. Okay, they weren't wiped out. That's an order of extinction. The goldenoids, they're here again, and that's the final straw for them. After this extinction, they're out. They're gone. They don't make it through. And then there are certain bivalves that also went extinct at this time frame. Goodbye. Why? Why did everyone go extinct? Well, probably one of the biggest events going on at this time was the formation of the Atlantic Ocean. We see a massive outpouring of lava, and we have what is referred to as the Central Atlantic Magnetic Province. Yeah, easier that way. So what would happen is that you get this massive outpouring of lava, and again, carbon dioxide, warming, rising sea level, put it all together. All right, finally, the last one, the end Cretaceous extinction. This is the one that most people are kind of familiar with because this wiped out the non-avian dinosaurs. Is that all that went extinct? Oh God, no. Oh God. But let's be honest, that's what we're all fascinated about. Dinosaurs went extinct. Oh my God, 65 million years in the making, right? Okay. Definitely a nasty event, but not the worst one. But probably the most famous one because of that. That's when the dinosaurs went extinct. So we look at the world. Does it look familiar? Absolutely. We're only 65 million years in the past. Remember how long ago? Right? If you want to think about the Earth's history like a clock, okay, this time frame right here, if it was a 24-hour clock, was about 2 minutes ago. Just for some perspective. Okay. So it looks familiar because again, we're starting to get toward the modern day. So you see all the familiar continents, you see familiar oceans, Australia, on the Antarctic, India. That's kind of a weird spot, isn't it? That's okay. Give it 60 million years and it'll be on the Asian time. Yeah. How fast do continents move? Anyone know? Slow. That's a good answer. I can totally agree with that. When you want to think about a crustal motion, average crustal motion, look at your fingernails. Okay. Now watch your fingernails grow. Okay. That's about how fast continents move, right? I mean, you do your nails every couple of weeks or so. And that's about how far a continent can move in that amount of time. So it's averages down to about 6 centimeters per year. And again, if you got 60 million years to play around with, yeah, India's gonna move. India's gonna. Anyway, so what are these guys? The for extinctions. This one is right here, the real big. This is what's called a rudis bivalve. Okay, rudis bivalves dominated the reefs. Okay, it wasn't plural, it was yes. So they dominated the oceans. Unfortunately, they went extinct. Okay. Non-avian dinosaurs. Okay, one of my personal favorites to have a T-Rex out there. Whatever. McAuliffe-Shepard. Must prefer McAuliffe-Shepard over dinosaurs. But yeah, they went extinct. Marine reptiles. Okay, mosasaurs, elastosaurs, ichthyosaurs, plesiosaurs, whatever. Families, orders. Don't get it. Okay. Ammonoids. Yeah, my ammonites didn't make it through. This is a different kind of ammonite, barely a roundish one that's going around. But it's kind of cool. When I pass this around, what I want you to look at is look at the suture, look at the lines that divide the chambers, and notice how intricate they are. Really cool. We can actually identify the species based on the pattern of the suture. So these are super cool. So take a look at that. And of course, we also have our flying reptiles, right? Pterodactyl, like walrus and stuff like that. They also do. So, what caused it? Well, again, we are familiar with the idea that yes, there was an asteroid impact at this time. Okay, we know that there was an impact. We have ample evidence. We have a layer of iridium that's found through various clay layers around the world, dated back at 66.4 million years ago. That was found back in 1980 by a team of Alvarez, Mitchell, and Massaro. Alvarez and Alvarez were actually a father-son team. One was a physicist, one was a geologist. One definitely had more fun job. Geologist. Sorry, Dave. But yes, so they discovered a layer of iridium, or rare elements, in the layer of clay that was attributed to an asteroid impact. Okay. But the thing is, we already had extinction going on. We already had, things going on that were starting to lead to some kind of an event happening. This was probably just the final straw that led to the extinction. What we see is that the planet was cooling down. Okay, although we did have one of our large igneous provinces that did erupt, called the Deccan Traps, and that probably led to a quick burst of warming. So we certainly have that to consider. And when we look at things like dinosaurs, their diversity was definitely dropping. Okay, they peaked about 50 million years prior to this event, and they were showing signs of decline from there. So they're probably already on their way out. But more than likely, the asteroid impact itself most likely led to the final demise. And it's an interesting event to think about. What would have actually happened when the Earth was struck by a large object? So the object itself was probably about 10 kilometers in diameter, about 6 miles, about the size of Mount Everest. Okay, so this object came in, didn't come head in, it came in at more of an angle, and struck around modern-day Yucatan Peninsula. Okay, we found the crater, we know it's there, and one of the things that we see north of the impact point are tsunami deposits, large chunks of debris that were being carried by a wave away from the impact point. You can imagine how big a tsunami was. It was probably a good 1,000 feet tall. So yeah, a little scary right there. So we have this big tsunami. The impactor hit a bed of mineral that we call gypsum. Now, gypsum is a sulfate mineral. And so the sulfate from the gypsum would have been injected into the atmosphere. And as it got into the atmosphere, it would have mixed with water. Well, you mix sulfate, you mix water, what do you get? You get sulfuric acid. Suddenly it's raining sulfuric acid, a lot like what happens on Venus. Not fun. Sulfuric acid also blocks sunlight. So this would have enhanced the cooling event that was going on. And not done yet. Not done yet. Not only did it throw all that sulfate into the atmosphere, it also threw huge quantities of rock and whatever else out there as well. So all that debris goes high into the atmosphere and eventually rains back down. Now keep in mind, the planet's rotating. So as all this is going on, the debris comes back down. It doesn't land around the crater, it lands in what will be modern day Africa, which is covered by forests. And those forests are suddenly getting bombarded by huge quantities of debris. That's flaming debris. Massive wildfires. Lots of smoke. All into the atmosphere. Yeah, not a good day. Not a good day. So, yeah. So the asteroid impact definitely kind of fits. Now, currently, today, we are in what is being referred to as the modern extinction, the sixth mass extinction. Okay, sometimes referred to, or currently trying to be being referred to as Anthropocene extinction. This is something that's going on right now. We definitely see enhanced extinction events, or enhanced extinction going on. We look at some of the critters that have gone by recently, the past 200 years. You have the passenger pigeon, you have the Tasmanian wolf, you have the western black rhinoceros, you got the dodo bird, and every one of those is linked to human activity. So we have something going on right now that is leading to an enhanced rate of extinction. Right? We have rapid global warming going on because of excess CO2. We have a lot of pollution, whether it be in the groundwater, in the oceans, the atmosphere. That's enhancing extinction. And then, of course, we have overpopulation. There's 7 billion people on this planet. You got to feed them. They need water. They need somewhere to live. But when they do that, they start pushing animals out and other organisms as well. So it's very likely that we are in the midst of the sixth mass extinction. Let's go. Questions? Was a competitive environment? Anywhere you have multiple species working to get the same resources, that would be competitive. So if it's non-competitive, that means that the organisms move somewhere where they don't have other things fighting with them for those resources.
How does modern extinction? What's our timetable?
That's a good question. That really is a good question because there are folks that humanity was responsible for the extinction of the mammoths, right? And the mammoths went extinct around 12,000 years ago. So it's really kind of hard to tell where exactly is this starting. Should we start at the Industrial Revolution, where we start seeing large CO2 amounts going into the atmosphere, and that's when we start to see the planet warm. It's really kind of, there's a lot of differing opinions on that right now, unfortunately. So I don't have to answer that.
Is it we at a place where this is reversible, or that's the point of no return?
As CO2 levels continue to rise, we're going to continue to see warming, and that's going to either that's going to continue to elevate the extinction rates. Can we stop it? I mean, we certainly decrease CO2 emissions and slow down this global warming. So possibly. The problem that you're into is that during extinction events, the organisms that tend to go extinct are what we call specialists. Those that are very specialized for a specific environment, like a panda bear, right? What do pandas eat? Bamboo. Do they eat anything else? No. What happens if you went on with bamboo? Pandas, right? So they are a specialist. What about a cockroach? What do they eat? Whatever they want, right? So those are more generalists. So generalists will make it through extinction events. Specialists tend to suffer. Once the extinction event is passed, whatever the generalists are left over, they're then going to diversify, and then we start seeing specialists develop from that.
So you don't have any unique cause for the mammoths?
It could be, a lot of people say it was overhunting because of humanity, which I mean is possible, but we're not completely sure about that. There is some evidence to suggest that they were on their way out. The planet was already going through a warming phase anyways, which probably just pushed them too far north to the point where they couldn't survive. So humanity may have had something to do with it, but I don't think it was overall cause. I think it was just climate change. So.
How does a volcano start?
How does a volcano start? When we talk about volcanoes, I'm going to try to keep this brief, okay? We talk about volcanoes, we talk about two kinds of volcanoes. We have what are called composite volcanoes and shield volcanoes. Composite volcanoes form along plate boundaries. Like you think about the west coast of South America, like the Andes Mountains, very volcanically active. And the reason that we have that going on is because there's ocean crust, which is going on underneath the continents, and then melts, creates the magma, which then rises to the top and then starts to erupt. As long as that's an active boundary, the volcanoes are going to continue to erupt. So once you initiate one of those types of boundaries, that's when you can initiate volcanic activity. When it comes to shield volcanoes, we think about something like Hawaii. Okay, Hawaii is a large island which is continuously growing, but the thing is that the plate on which Hawaii is located is migrating over the top of what's called a hotspot. Okay, so the hotspot is extruding magma onto the surface, and once the main island moves away from that hotspot, a new island is going to form, and that'll be the next major island for Hawaii. So a little bit of real estate advice: if you've got 10 million years, buy a little patch of land, over down to the southeast of Hawaii, and 10 million years, you're going to have yourself a nice island. Okay.
You talked about ocean circulation in one program.
Yep.
So what can change like ocean circulation?
Something just as simple as the continents moving. When you look at the modern world, I'll pull up the okay. So, like for the Cretaceous, for the Cretaceous, we're going to end up with the modern world. Right now, here, there's no land in South America and North America, so water can simply move right through here without too much of an issue. But the second you grow Central America, South America moves a little bit further north, you go to the Isthmus of Panama, that's going to block off that ocean circulation. That actually can lead to extinction. We actually looked at the fossil record for about 3 million years ago, and we see there was a rapid change roughly 3 million years ago because of the sudden change of that pattern.
So does the circulation then have an impact on the continents actually moving? Like does one affect the other?
No, the water is restricted to the surface. The continents themselves move as a result of convective cells down in the Earth's mantle. And again, very slow process. But the continents are going to move the ocean. So. Yeah. Yes. Yeah.
For the volcanoes becoming active that are not that before, because the tsunamis to be more widespread.
Not really. When you look at the entire ring of fire, it's actually surrounded by what are called convergent boundaries. South America is part of the overall ring of fire. So in all those areas, you have ocean crust going on underneath either continental crust or ocean crust. And so what that does is it forms kind of feature that's called an island arc. And so as the name implies, an arc-shaped line of islands. If you look at Japan is a really good example of that, but the Philippine Islands, Indonesia and Java, the Aleutians, and the Caribbean, you see it as well. Where was I going with this? I just totally lost my train of thought. I'm so sorry.
Ring of fire.
Ring of fire. There we go. Thank you. So it's all part of this ring of fire. And so this is going to lead to volcanic activity, not necessarily increased tsunamis. That just happened to be a really severe one. You actually had a very serious displacement of the crust that was going underneath, and you had a large block which opened up and dropped. And when the block drops, the water above drops as well. And suddenly something's going to fill it in. And then when all the water comes together, boom, tsunami as a result.
So extinction probably aren't bad because the Earth is a living object and it's going to happen no matter what.
It's inevitable. I mean, when you really think about it, 99% of all life on this planet has gone extinct. We're just the most recent version. So yeah, extinction is, I don't know if I want to say it's a guarantee, but it's pretty much guaranteed. Humans are gonna be more extinct eventually. What are we gonna do? We'll probably, if we'll change to something else different, you know, we're gonna lose our little toe. Little toe is totally useless. So, yeah, we'll lose our little toe, we'll be a totally different kind of human. But yeah, but no, it's absolutely extinction, this is a necessity. If you didn't have extinction, I mean, think about how many species of organisms there would be on this planet, and we still have to compete with the T-Rex. Not fun. Not fun, I'll pass, thank you.
We got about 9 minutes.
Okay.